Alrighty, today we are going to look at the topic of solution stoichiometry, one of my favorite topics. So we already have a good background in stoichiometry, so now we're just going to meld it together with our understanding of solutions and some of those calculations. So here we go. Many chemical reactions take place in aqueous solutions. Okay, so aqueous just means it's something that's been dissolved in water. Did I spell that right? Oh, yes, I did. Aqueous means the solid is dissolved in water. In solution stoichiometry, or solution stoich, we use information about the concentration or masses of the reactants to calculate the masses of the products. Okay, so it's still stoichiometry. We're still using the balanced chemical equation to kind of figure out how much of a substance might be formed. The only difference was in the stoichiometry unit, we were always dealing with grams or moles of a substance and making predictions about grams or moles of some other substance in the reaction, like a product, for instance. Now we're going to start to combine that with solutions. So we might know the concentration and the volume, for instance. So write a balanced equation for the reaction is always going to be our first step. Just like in stoichiometry, we would always do that first. Then we're going to change the given value, either the concentration or the mass, to moles. Okay, so this is where things change. So normally we would just either be given mass or be given moles. Here it's going to be something where we're going to be required to use this. The concentration formula sort of rearranged to solve for moles. Then change the number of moles of what you're given to the number of moles of the products by using the mole ratio in the chemical equation, and then change the number of moles of products to mass in grams. Okay, so steps really don't mean anything unless you apply them to a particular example. So let's do that so that you can see what I'm talking about. So here's an example. We have 10 milliliters of a 0.2 mole per liter solution of sodium hydroxide, and that's reacting with 10 milliliters of a 0.1 mole per liter solution of iron 3 chloride. Calculate the mass of iron 3 hydroxide produced. Okay, so this is clearly a chemical reaction. We've got sodium hydroxide reacting with iron 3 chloride. We're told one of the products is iron 3 hydroxide. So let's write out the balanced equation first, and then we'll decipher these values next. Okay, so sodium hydroxide is NaOH. OH is the hydroxide ion. Plus 1 charge, minus 1 charge, okay, plus iron 3 chloride. So the 3 tells us that iron has a plus 3 charge, chlorine has a minus 1 charge, so I'm going to put a subscript 3 here. And that is going to produce, well, we're told one of the products is iron 3 hydroxide. So hydroxide, we already said, has a negative 1 charge. So when it combines with iron 3, we need to do this. Now, this would be a double replacement or double displacement reaction, meaning these two compounds switch partners. So we've already combined iron and hydroxide. So now we want to combine sodium and chlorine. Remember, another way to do double displacements is your inner ions go together and your outer ions go together. You always do positive ion followed by negative ion. So for sodium and chlorine, that would be NaCl, plus one charge, minus one charge. So it's good to go the way it is. Now we're not balanced here. We've got 3 hydroxides and only 1 hydroxide here. So I'm going to put a 3 there. And then that gives me 3 sodium. So I'd need to make 3 over here. I also have 3 chlorine, so that takes care of the chlorine at the same time. Iron is good the way it is. So everything is balanced at this point. Now, originally, what you would have done in stoichiometry is you would have been given a question very similar to this, but you wouldn't have been given volume and concentration for each substance. You would have either been given just moles of this substance and moles of this one, or grams of this substance and grams of this one. So we are now saying, well, this is a solution. I have 10 milliliters of the solution, and I know that this is its concentration. So this is actually a very realistic problem you would have to solve in the lab, because often when we mix 2 substances together, they're in solution form. It's been some sort of solid dissolved in water, and we know the concentration of the solution, and we can measure out the volume in a graduated cylinder. So this is quite a realistic thing that you would do in the lab. Okay, so we have 10 milliliters and we have this concentration of sodium hydroxide, and we have another 10 milliliters of this concentration of iron 3 chloride. Okay, now what we know is if we're going to predict the mass in grams of iron 3 hydroxide produced, we have to figure out which of these 2 is the limiting reactant. The limiting reactant will always determine how much product gets produced. But before we can do that, we have to get these numbers, we need to convert that into moles so that we can work our way towards grams of product. So what I'm going to do here is I'm going to take, well, if I know concentration and volume, I can use C equals N over V to solve for number of moles. So I'm just going to rearrange that to N equals CV. Okay, so for sodium hydroxide, I would take the concentration of 0.2 moles per liter, and I'd multiply by the volume of 10. Now it's 10 milliliters. Because this is moles per liter, that needs to be in liters. So remember, you want to zip your decimal place over 3 spots. So that would be 0.01 liters. And that would give you 0.002 moles. And this is my sodium hydroxide. Oops, sodium. Okay, now I'm going to do the same thing for iron 3 chloride. I also know the concentration and the volume of that. So the concentration is 0.1 mole per liter. The volume, again, it's 10 milliliters, so that's equivalent to 0.01 liters. So when I multiply, I get 0.001 moles. And that is the other reactant, FeCl3. Okay, so that is really the only new step in this stoichiometry problem that you wouldn't have done previously. From this point forward, it would work just like our previous stoichiometry problems. We need to figure out which of these 2 reactants is the limiting reactant. Now, this was a topic covered, I did not have a video. You didn't get like a live lesson on limiting reactants. So if that was a sort of iffy topic for you at that point in time, because I didn't like fully demonstrate it to you, then now is a good time to revisit it and review it, because it's quite important. Okay, so let's do this. We want to figure out which one of these limits the reactant. So just to review what a limiting reactant is when you mix two things together and they react, one of the two is going to get used up first. Okay, it's going to run out. Whichever one gets used up first is going to cause the reaction to stop, right? Because once one of the reactants is gone, there's nothing left for the other reactant to react with. And I'm not saying it's this one. I can't remember which one it is till we start working on it. But one of the two runs out first, and that's going to cause the reaction to stop. No new product can form once one of the reactants is gone. So whichever one gets used up first, we call the limiting reactant. It limits the reaction and it determines how much of each product will form. Okay, so the way you can figure out which one is the limiting reactant is you can convert both reactants into an amount of product. And then you can compare the two amounts of product to see which one produces the lower amount. The limiting reactant will always produce the lower amount. Now, the important thing here is that you convert to the same product. Now, to save yourself time and effort, you can choose any product you want out of the two, but it makes the most sense to choose the one that the question's asking you about so that you don't have to do extra work, because these are long, time-consuming problems as it is. So make it easy on yourself. So the question is asking us about the mass of iron 3 hydroxide. So I'm going to convert to iron 3 hydroxide for both reactants because I know I'm going to need to know something about that anyway. So I'm going to take my 0.002 moles of sodium hydroxide, and I'm going to convert it to eventually grams of iron 3 hydroxide. So my first job is, if I'm in moles of NaOH, I can get to moles of any other substance using the mole ratio. So I don't want to be in moles of NaOH, so that's why I put it on the bottom. What I do want to be in is moles of iron 3 hydroxide. So I'm going to put that up here. Okay, now into this is our mole ratio step. So into this, we put the coefficients from the balanced equation. So there's no coefficient in front of iron 3 hydroxide, so I'm going to use a 1. There's a 3 in front of sodium hydroxide, so I will put a 3 there. So moles of sodium hydroxide will cancel, and I'm going to take it one more step because I know I have to figure out grams of this substance. So I'm going to take it one more step and go from moles of iron 3 hydroxide to grams. Okay, so this, I'm going to use the molar mass. So how many grams of iron 3 hydroxide are in 1 mole? So for that, you'd take the mass of iron plus 3 times the mass of oxygen plus 3 times the mass of hydrogen. And at this point, you've done molar mass so many times, I don't need to see it written out. You can just do it in your calculator and plop it in there. So that's going to cancel. And now I'm going to just multiply my way through. So 0.002 divided by 3 times 106.88. And that would give me 0.00, oh, sorry, one too many zeros. 0.07 grams, and that is going to be of the FeOH3. Okay, so this is not meaningful yet until we work our way through the second reactant. So I now need to do the exact same thing with the 0.001 moles of iron 3 chloride. And I'm, in the end, going to compare the two amounts. So I want to go from moles of iron 3 chloride to moles of iron 3 hydroxide. Okay, I already checked to see that there was no coefficient here. There's also no coefficient there. So this mole ratio step will actually do nothing to change your end result. It's just more of a record keeping step that we're switching over from iron 3 chloride to iron 3 hydroxide. And finally, let's get it into grams. So we'll use the molar mass. So how many grams are in 1 mole? Well, luckily we already figured that out. Okay, so really all there is to do here is 0.001 multiplied by 106.88, and that works out to 0.11 grams of the iron 3 hydroxide. So what does this mean? Well, we've worked our way with both reactants all the way to the same product. And this is telling us that sodium hydroxide produces 0.07 grams of iron 3 hydroxide, and iron 3 chloride produces 0.11 grams of iron 3 hydroxide. So the reactant that produces the lower amount is the limiting one, because that's the one that would run out first. Okay, so this is the lower amount, therefore NaOH is my limiting reactant. Okay, so why is that important? Well, we'll see, because it's the limiting reactant that tells us how much product is formed. Once it's gone, the reaction stops. Okay, so this, I just included this all in the previous step. So let's just say done in previous step. That's kind of messy. And what is the mass of iron 3 hydroxide produced? Well, we calculated that in step 2. So you always choose the amount produced by the limiting reactant. So it's the lower amount, which is the amount produced by the limiting reactant. So this is how much, 0.07 grams is how much iron 3 hydroxide is actually produced in this reaction. So I'm going to say 0.07 grams of iron 3 hydroxide is produced. And I'm just going to put done in step 2. All right, so that's kind of the final answer you want to get to. Now, I included a video of this demonstration. So normally I could do this for you in the classroom just so you could see. It's kind of a neat reaction to watch, but we're going to work through this reaction with the stoichiometry. The video, if you click on the link, I just put it on the Edmodo post, or you can access it through the notes. If you click on it, it just shows you what this reaction actually looks like. So I've got 10 milliliters of a 0.01 mole per liter solution of lead 2 nitrate, and I'm mixing that with 10 milliliters of a 0.1 mole per liter solution of potassium iodide. What is the mass? Calculate the mass, which is always going to be in grams, of lead 2 iodide precipitate that should form. Now, precipitate just means when you mix these two solutions together, one of the two products forms a precipitate, means it's not soluble. So it kind of forms like a solid that will eventually settle to the bottom of the beaker. And it first appears kind of like jelly-like. So it's quite noticeable when a precipitate forms. It looks like a blob of jelly-like substance, and then over time as it sits, it settles to the bottom. So our first step is, let's write out the reaction. So we've got lead 2 nitrate. So nitrate's got a -1 charge. So I'm going to put a 2 here. And I'm going to combine that with potassium iodide. Potassium's a +1 and iodine's a -1. It's going to look like that. I've been told one of the products, but even if I wasn't, I could figure them out because this is two compounds mixed together is going to be a double displacement. So just like before, I'm going to do inner ions and outer. Okay, so lead 2 iodide would be PbI2, and my other compound would be potassium nitrate, +1 -1, so it can just stay like that. To balance this out, I've got 2 nitrate ions here, so I need to put 2 here. And then to fix the potassium and iodine, I need a 2 here. So let's go to the where we calculate the number of moles of each reactant. So I'm going to start with the lead 2 nitrate. And I'm going to use N equals CV because I have the concentration and the volume of the lead 2 nitrate. So the concentration is 0.01 mole per liter. The volume's 10 milliliters. I want to express that in liters. So I get 0.0001 moles. And I'm going to do the same thing for Ki. So I have a concentration of 0.1 mole per liter and a volume also of 10 milliliters or 0.01 liters, which would result in 0.001 moles. Okay, so now that I have dealt with this solution part of it, we just go right back to our stoichiometry and we're going to work our way from moles of each reactant to grams of the product that we're interested in. So the question is asking us about lead 2 iodide. So I'm going to convert to lead 2 iodide because that'll make my life a lot simpler. So I'm just going to put limiting reactant. Just to kind of, you don't have to do this, it's just sort of to break down the steps that we're doing. So I'll start with the lead 2 nitrate. I have 0.0001 or 1 × 10⁻⁴ moles of lead 2 nitrate. So because I'm in moles, I can use the mole ratio step to get into moles of lead 2 iodide. Now remember, in here in the mole ratio step, you use the coefficients from the balanced equation. So lead 2 iodide, there's no coefficient. Lead 2 nitrate, also no coefficient. So again, this mole ratio step here is not going to affect your answer. It's just kind of record keeping to show that we've switched to a different substance. So moles of lead 2 iodide on the bottom, and I'm interested in the mass of lead 2 iodide. So I'm going to go to grams. This is going to be the molar mass step. So how many grams are in 1 mole? So I'm going to add the mass of lead to 2 times the mass of iodine. And that turns out to be 461 grams. So my only calculation here is 0.0001 times 461, which equals 0.046 grams of lead 2 iodide. Okay, so now let's do the same, starting with the other reactant. So the other reactant, I have 0.001 moles of Ki. Okay, so I'm going to switch over from Ki to PbI2. Okay, let's check the balanced equation. PBI2, there's no coefficient, but for Ki there's a 2. Okay, and finally I'm going to go from moles of PBI2 into grams using the molar mass. Okay, so 0.001 divided by 2 multiplied by 461 is 0.231 grams. Okay, so when we compare these two, we can see that lead 2 nitrate produces less of the product, less of the lead 2 iodide. So that's the value we're interested in, the lower amount, and the lower amount shows us that this is our limiting reactant. So I'm just going to put LR for limiting reactant. So all my math is done. I've done all the calculating I need. Now I can just say, well, therefore, 0.046 grams of PBI2 is produced. Okay. A couple more examples. So this one is a tiny bit different in that you've got a mass of one of your reactants, because zinc is just a metal, so we have its mass in grams, and that piece of zinc metal is being placed into a solution. So the solution, we have the volume and the concentration of the solution, and it's copper 2 chloride solution. So we're looking for what mass of copper metal is produced. So we still want to break apart our two reactants and convert them from whatever they're in into moles. So in the case of zinc, because it's in grams, I just convert it to moles using molar mass. Okay, so the molar mass of zinc is 65.39, and that would result in 0.153 moles. Okay, for the copper 2 chloride, whoops. I'm going to have to use, because it's a solution, I would need to use N equals CV. So I take the concentration times the volume, make sure it's in liters, to get 0.1 moles there. Now, so I have both reactants switched into moles. What I forgot to do to start with was write out the balanced equation. So I've got zinc being added to copper 2 chloride. I know that in this case, this would be a single replacement reaction. So one of the products we know is copper. Zinc and copper are your two metals, so they're switching places. So I've got copper, and that's going to match zinc and chloride together. Zinc is a +2 charge, so it would be ZnCl2. Now this happens to be balanced just the way it is, so I can leave it. And now I'm going to work on figuring out which one is the limiting reactant. I'm converting to copper because that's what the question is asking me for. So I'll start with zinc. And I'm going to go from moles of zinc to moles of copper. That's a 1-to-1 ratio because there was no coefficients needed to balance the equation. And then I'm going to go from moles of copper to grams. This is the molar mass, and copper's molar mass is 63.55. So when I calculate that, I get 9.72 grams of copper. I'm going to do the same thing with the copper 2 chloride. Got 0.1 moles CuCl2. I'm going to convert to moles of copper. Again, it's 1 to 1. And finally to grams. Okay, so when I multiply, I get 6.36 grams. So when I compare these two, this is definitely the lower amount, meaning this is my limiting reactant, CuCl2. Therefore, I'll just write it over here because I'm running out of room, 6.36 grams of copper is produced. Okay, one more to go. This is going to be similar to the previous. So we've got a solution mixed with just a chunk of metal. So we've got a 0.5 mole per liter solution of copper 2 sulfate, and we have 100 milliliters of that. And we're dropping in a 10-gram chunk of aluminum. And then we're going to calculate how much copper is produced. So mass of copper produced in this single displacement reaction. So let's start with our balanced equation. So copper 2 sulfate would look like this, plus 2 charge minus 2 charge. We're adding that to aluminum. Single displacement, aluminum's a metal, so it'll switch with copper. So that's going to give us copper and aluminum sulfate. Now aluminum's a +3 and sulfate's a -2. So we've got a crisscross there, like that. So we do need to balance this. Start with aluminum, we'll put a 2. Sulfate, there's 3 of them, so let's put a 3 here, and then we'll need a 3 there. And that should do it. Okay, so again, let's deal with our reactants and make sure they're both in moles. So the copper 2 sulfate is a solution, therefore I'll use N equals CV. I've got 0.5 moles per liter for a concentration and 100 milliliters or 0.1 liters for a volume. And that's going to give me 0.05 moles. For the aluminum, because it's just a piece of metal, I just have a mass. So I'm going to convert that mass into moles using molar mass. And this would be 26.98. Okay, so 0.371 moles. Now I'll do the limiting reactant step. Starting with copper 2 sulfate, 0.05 moles of CuSO4. Let's get that into moles of the product we're interested in, which is copper. So if I look to my balanced equation, I've got a 3 by copper and a 3 by copper 2 sulfate. So this step really doesn't change anything. And then I'm going to go from moles of copper to grams using the molar mass. So again, 63.55. So when I calculate that, I get 3.18 grams. That would be of copper. And I'll do the same starting with aluminum. So moles of aluminum, 2 moles of copper. I know there's a 3 there. For aluminum, there's a 2. And then convert to grams. Okay, and that one would work out to 35.37 grams. Okay, so significantly less copper is produced by the copper 2 sulfate, which means the copper 2 sulfate is the limiting reactant. And my final statement would be, therefore, 3.18 grams of copper is produced. Okay, so you can work on the solution stoichiometry worksheet so that you can practice some of these questions on your own.